Our last lesson for our quadratic unit deals with word problems, specifically projectile motion. Let's take a look at a real live projectile motion.
Steph, no timeout with 6 and 5. Curry for the lead.
I want you to notice the shape that the basketball creates when he throws it to the goal.
Curry splits the defense behind the back. Fires a three. Oh, he puts it in.
Notice it is a downward parabola.
Certainly the highlight play of the day. Stephen Curry knocks down the three. The Warriors. Now here is Curry. The step around move to Livingston. No look, flip back. Oh my goodness.
Okay, so our definition for projectile. A projectile is an object that rises and falls under the influence of gravity. So in the example in the video, as well as what we have on the screen, the basketball is the projectile. Projectile motion is the height of that object as a function of time. So as you can see here, our basketball is launched at 6 feet. So let's recall the x-axis in projectile word problems represents time in seconds. So we're always going to have our seconds on the x-axis, and then the y-axis will represent height in either feet or in meters. So you can see at 0 seconds, the basketball was launched at 6 feet. Then it reached a maximum height of 12 feet in almost 2 seconds. Then we come over here as it's coming down, and it's 6 feet again, but this time has passed by, and that's a little bit above 3 seconds. So our basketball is at 6 feet again, and then it lands on the ground at about 3.75 seconds. So we're always talking about time and compared to the height of the object as it's being thrown or launched. There are 3 critical points of our parabolas that we will discuss in each of our word problems. Let's start out with our y-intercept. The y-intercept is the point in where our graph intersects the y-axis. And in this case, our y-intercept intersects at 0.6. Again, our basketball started, its initial height starts at 6 feet. So our y-intercept is 0 in 0 seconds. It is 6 feet. Now let's move on to the vertex. The vertex, in this case, is a maximum point. When we're discussing projectiles and projectile motion, our vertex will always be a maximum point because our parabolas are going to turn down. This vertex tells me that in a little bit more than between 1 and 2 seconds, the basketball reached its maximum height, and that height is 12. So always keep in mind that your vertex has 2 values, an x and a y coordinate. In our word problem situations, our x is always going to represent seconds and our y is going to represent the height. Now let's talk about the roots. The roots are the x-intercepts. This is when the object is on the ground. In this situation, our first root you can see is negative. And remember, our x-axis represents time, so you really cannot have negative seconds. That does not make any sense. So this root is irrelevant. When your object is not launched from the ground, like in this case, one of your roots will be negative. Now let's look at our positive root on the right side here. This value tells me how long it took for the object to hit the ground, which would be a height of 0. So in about 3.75 seconds, that would be your x, our height is 0. It is on the ground. Now let's put all the formulas together. Make sure you have these written in your notebook, and let's go over them again. Your y-intercept for our word problems for projectile motion is the height in which the object is first launched. The vertex is going to tell me the amount of seconds it takes the object to reach the maximum height. And then we have our roots. The positive root is going to be how long, how many seconds it takes the object to hit the ground. Sometimes our root may be 0, 0, which means it was launched from the ground. And then the positive root will always be the amount of time it takes for the object to hit the ground. We will normally use the quadratic formula. Most of the time, our quadratic equations will not be factorable, so we will have to use the quadratic formula. Projectile motion involves objects that are dropped, thrown straight up, or thrown straight down. So you can see in this first case, an object is just dropped. The second case is thrown straight up and comes straight back down. However, you do see a narrow parabola because even just a split second has gone by for the object to go up and to come down. Factors that influence the height of the object is the height from which it was dropped or thrown, whether it's upward or downward velocity is involved, and then a pull of gravity. Here is the general formula. There's really no need to write this formula down. I will tell you when you should write a formula down. But let's just go through the components that create this quadratic equation. Your h of t represents your height over how many ever seconds. We have an a value, which is our acceleration due to gravity. We'll talk about that on the next page. So now you remember that we have an a value, and then our v sub 0, this is your initial velocity, your momentum. This is considered your b value. And then we have our initial height, the height in which the object is launched or thrown, and that would be your c value. So this quadratic equation is the same equation, it's standard form that you're used to. Our t value is going to represent time, and our h represents height. Okay. Now, let's talk about the gravity. Since the acceleration due to gravity is approximately 32 feet per second squared, or 9.8 meters per second squared on Earth, this is going to be where we get our a value. All you need to know is that if your word problem is dealing in feet, you're going to use -16. Negative because it turns down, and then 16 because we're taking half of the gravity. So this is if you're talking about feet. If the word problem talks about feet, you should just automatically think, oh, -16. And then if your word problem is dealing with meters, you're going to use -4.9. So let's take a closer look, and you can jot these down. So in your notebook, you need to write objects that are thrown. There is a certain velocity, like we've talked about, that accompanies the launch. So I would write objects that are thrown. When you're working in feet, here is your equation. Objects that are thrown when working in meters, here is your equation. Again, have these available when you're trying to write your equations for word problems. The next slide is when objects are dropped. When you have an object that's dropped, it's not thrown, there is no initial velocity. So again, in your notebook, write objects that are dropped have no initial velocity. Therefore, there is no b term. This middle term, it is 0, so you don't have a term for there. So here is the equation you're going to have. It's pretty much you have your a value and your c value. So again, when objects are dropped and they're not thrown, there is no initial velocity. When you're dealing with feet, you're going to use this equation, and when you're dealing with meters, you're going to use this equation.